All right, we're going to add a new trick to our derivative taking bag. Today we're going to talk about how to take the derivative of composite functions. Remember, a composite function is when another function is put inside of the function itself. And the way we write this technically is if we have fog prime, which is the composite of f and g prime, or the derivative, is you take the derivative of the outside function, leaving the inside function intact, times the derivative of the inside function. Now, this particular way here, to me, looks a little bit confusing. This is probably a more common way to write it, and what it means is you're taking the derivative of this function with respect to x, and so you take the derivative with respect to the inside function times the derivative of the inside function with respect to x. Now, what in the world does that mean? So let's do some examples, and you'll see that it's really not that complicated. So let's say we have f of x is 7 times 3x minus 6 plus 10. So what you can say to yourself is, well, I have this inside function, and this inside function we're going to call u. Now, this u substitution that we're going to use is really common for a lot of calculus techniques. So if you are having trouble with that, make sure you go back over and figure it out. Ask some questions and work some extra problems so that you can make sure you understand how we're substituting this in. So if we have that u is our 3x minus 6, it's our inside function, then f at u is 7u plus 10. Well, that's a pretty easy derivative to take. So if we want to take the derivative of that with respect to u, it's just 7. And here, we've got to have our du dx, and that's 3. So if we want to know what df dx is, the derivative of this function with respect to x, we just took the derivative of the outside part, 7, times the derivative of the inside part, 3. So the derivative is just 21. Okay, so we look at these functions as outside, inside. What's inside, what's outside? Take the derivative of the outside part, and then take the derivative of the inside part. Now, could you distribute this, simplify it, and then do this? Of course you could. That would be even easier. But we're using it for illustrative purposes because when we get to some other functions, it's a little bit harder. For example, if we have the square root of x plus x squared, we know how to find the derivative of the square root of x. We use that power rule. But when we throw in more stuff on the inside, that causes us problems. So we need to ask ourselves, what's the inside function? What is inside that's causing us more problems? Well, our inside function is this x plus x squared. So then our outside function is just the square root of u. So that square root is what we're going to start with, taking the derivative of. So what we do is we take the derivative, dy dx, or you call it df dx if you want. So we take the derivative of the outside part, but we leave this u intact. So we bring down our power, what's u, and then lower it by 1, power rule, times, and then we take the derivative of the inside part. And then we can just simplify. So we took the derivative of the outside part here, took the derivative of that, and then multiplied it times the derivative of the inside part. Now, sometimes you're going to have multiple outsides and insides, so make sure you're kind of looking for all the different pieces and breaking it down. Let's try another one. What if we have a function sine of 2x? Okay, so what's our inside part? Well, the inside is 2x, because we know how to take the sine of an angle, just the sine of x, or the sine of theta, or whatever. We know how to take the derivative of that. But when we have extra stuff in there, that's when it gets complicated. So our outside function then is the sine of u, which we know how to deal with. So the derivative is the derivative of this outside part. So the derivative of the sine is cosine of our u, which is 2x, times the derivative of the inside part, which is 2. So neaten that up a little bit, and we have our answer. What about this one? Go ahead and pause it and try to do this one on your own, and then check it. So we look for our inside function. What's our inside function? It's 1 plus x squared. So that means our outside function is u to the 10th power. So our derivative, take the derivative of the outside part, 10 times our u, and then lower the power down 1, times the derivative of the outside part, or the inside part, sorry. So that gives us 20x times 1 plus x squared to the 9th. So we've got the derivative of the outside times the derivative of the inside. Now, sometimes it's just a little bit more complicated. Say we have this position function. So our inside is t squared over t minus 1, and our outside is u to the 4th. So the derivative would be, use the power rule here, so 4 times our u, bring the power down 1, times, then we take the derivative of the inside part. So we have bottom times the derivative of the top minus top times the derivative of the bottom all over the bottom squared. Alright, so now we just need to simplify. So here we've got 2t squared minus 2t minus t squared, which is just t squared minus 2t, which is t times t minus 2. Alright, so we have 4 times, this is t to the 6th, and then there's one more t there, t to the 7th, times t minus 2, all over, we've got t to the 3rd and t to the 2nd, so t minus 1 to the 5th. So make sure you understand how to simplify all that, because that should be old hat by now. So we took the derivative of the outside part, and then the derivative of the inside part, and even when pieces take more steps, that's still how you do it. Now there's one other thing that I just want to mention so that you've been exposed to it, and that's parametrics. Remember, we talked a little bit about parametrics. We're not going to really dwell on those very much, but we talked about parametrics where we had these two functions that were dependent on a different variable. So if we have x of t, it's some function of t, and y of t, some function of t. And if we want to take those derivatives, we would get a derivative of x with respect to t, and a derivative of y with respect to t. But what happens if we want the derivative of y with respect to x, like we do with most things? Well, basically, you have to use that chain rule, and you see that dy dt is dy dx times dx dt. See here, these middle parts, just like with our chain rule, we've got to get those to match so that we end up with that. And so that means that dy dx is dy dt divided by dx dt. So we take this, it's multiplied times there, divide it over, so that we can just solve for the dy dx. So to find our derivatives our derivative with respect to x. Of the parametrics, you take the derivatives with respect to t and divide them. So, for example, if we have x is 5 sine t and y is negative 3 cosine t, then dy dx would be take the derivative of this y part. So the derivative of cosine is negative sine, multiply that times the negative, and you end up with 3 sine t, and then over the derivative of the x part, and the derivative of sine is cosine. So you could rewrite this as tangent of t. And yes, there's no x variable in there, but for parametrics, everything's dependent on t, and so that's why we're taking that derivative. Now, will we use this a lot? No, we will not use this very much at all. You just need to have seen it and make sure that you just write down somewhere on your spiral cards that to take the derivative of the parametrics, this is what we need. All right, hopefully we've got the chain rule down. Make sure you take the derivative of the outside times the derivative of the inside. No matter how many outsides and insides, you may find that you have more than one inside, and we'll look at some of those in class. So write down any questions you have. Make sure you've read section 3.6.